Thank you for joining me. So I have titled this, When Does a High Pass Filter Look Like an All Pass Filter? So in most of my videos, I try to teach you how to do something, or I try to share something that I recently learned, but it's usually geared towards how to get something done. But in this video, I just want to take a look at some shapes of some filters and see what is the nature of these shapes of these filters, and are there any similarities we can find between them? Okay, so let me make sure everything's working okay. Okay. So here we're looking at this piece of software called Crosslight. And what's fun about Crosslight is that we can just sort of have a playground for looking at filters. So what I'm going to do is I'm just going to turn on some filters, and we're not trying to get anything done, but let's just look at some shapes. So right now we're just looking at a microphone cable. So this is the magnitude of a microphone cable. It's completely flat, totally boring, right? What if I insert a high pass filter? So I'm going to enable a filter here. Pretty boring. Just a high pass filter, a Linkwitz-Riley, second order, 12 dB per octave, high pass filter at 20 hertz. Now I'm going to grab onto this handle and I'm going to move it up a little bit. And I'm going to look at where the cutoff frequency is. Right now the cutoff frequency is at 30.5 hertz. So 30 hertz is about here, and I can see that this is interesting. So where the cutoff frequency is at 30 hertz, we're down by 6 dB. I'm looking at the magnitude scale over here on the left. So minus 6 dB. That's interesting. So let me put my marker there. I've got this helpful little marker, so I'll put that at 30 hertz as well. And I'm going to turn on the phase graph instead. So here's the phase graph. And now as I sort of drag this guy around, I can see, that's interesting. So as I put in a high pass filter, the phase seems to be shifted up, right? So if I turn it off, we'll have completely flat phase, right? Just measuring a microphone cable. If I turn the filter on, okay, phase gets shifted up. That's interesting. Okay, high pass filter, phase goes up, little mnemonic device, maybe that'll help me. And so as I drag this around, I see that the phase shift is increasing, increasing, increasing. So let's pick a spot to put this on. Let's put this filter at cutoff frequency of 40 hertz. And then I'll put my little marker at 40 hertz as well. Let's see how much phase shift we have at the cutoff frequency. So it looks like 90 degrees of phase shift. Okay, now let's look at magnitude and phase together on the same graph. Okay, I know this can be a little bit confusing because they're the same color. But on the y-axis over here, we have magnitude. And on the y-axis over here, we have phase with 0 degrees in the middle, 180 degrees at the top, and negative 180 degrees at the bottom. And so I've got my marker here. And so now I can sort of watch these two things change at the same time. I can not only look at how the phase is changing, but how the magnitude is changing. So let's just review quickly. So I remember now I see at my cutoff frequency, I have minus 6 dB in the magnitude, plus 90 in the phase. So I grab my little handle down here, and I'm going to shift it up to, let's go up to 50 hertz. Okay, and then I'll put my marker up there, and we should see that everything has stayed the same, right? But at a different frequency. So minus 6 dB, plus 90 degrees. And now I'm just going to shift this around a little bit and see that that pattern continues to remain the same. No matter where I put my cutoff frequency, now at 100 degrees, right? So here's 100 degrees, minus 6 dB, plus 90 degrees in the phase. Okay, so just interesting to kind of to see that shape happen. So let's mute this guy. I've got another channel over here, and I'll unmute this guy. And let's just verify first. Okay, here's the microphone cable. And now let's put in a Linkwitz-Riley second order 12 dB per octave low pass filter at 20,000 hertz, way up here. So it's not doing much, but we can see it doing something. So it's rolling off the top of the magnitude display here, and here's the phase. So let me do these one by one again, just to make this clear. Here's the magnitude, okay? And if I grab this little handle and move it down, we see it's cutting off more. I grab it way down here. So we see this filter moving, right? It's filtering out more and more of the highs and leaving the lows. So we've got this stop band up here and this pass band down here, and our cutoff frequency now is here around 1500 or something. Okay, I'm going to drag this back up here, and now let's look at the phase. Okay, so we see that this low-pass filter is creating this kind of phase change, this phase shift. It seems to be pushing the phase down. So another maybe helpful mnemonic device for me is that when I turn on or insert a low-pass filter, I'm creating negative phase shift. So I can see this went down because it used to be flat, right? Okay, so as I drag this guy around, I can see that it gets more and more phase shift wherever that cutoff frequency is. And if I put this in a specific place, like let's put this at 6,000 hertz, and then I can drag this guy up to, where's 6,000? I can just type it in here, 6,000 hertz. Then we should be able to see something similar that we saw with the high-pass filter. Now let's look at magnitude and phase again together. So here's magnitude in blue, and here's phase in blue, but the magnitude one is a little bit bolder. That's how you can tell. Okay, so cutoff frequency is at 6,000 hertz, and my marker here is at 6,000 hertz, this cursor. And I can see that at the cutoff frequency, I have minus 6 dB in the magnitude, and minus 90 in the phase. So the only thing that's changed here between the high-pass filter and the low-pass filter is that the phase is now a negative number instead of a positive number. Remember, before it was 90 degrees of phase shift up, and now here with the low-pass filter, it's 90 degrees of phase shift down in the negative direction. So now let's turn these two on together, because I think it would be fun to sort of see them move together. Okay, so I know there's a lot of stuff on the screen now, but just remember, red is channel 1, and blue is channel 2. Red has the high-pass filter, blue has the low-pass filter. And so as I move this high-pass filter around, we can see it cutting more of this red channel, right? So I'll move it closer and closer. We're going to head for 1K, by the way, and I can see the phase changing here. And over on my second channel, as I bring down the low-pass filter, I can see these two things getting close to each other. And so let's go ahead and head over to 1 kilohertz. Now I'm not going to put them exactly on 1 kilohertz because I still want to be able to show you something. You'll see why in a second. On channel 1, I'll do the same thing. I'll head this high-pass filter up to 1 kilohertz. Now what can we expect? Well, we learned a couple of things. Minus 6 dB in the magnitude for this particular topology of Linkwitz-Riley. And we see that at the cutoff frequency, we have 90 degrees of phase shift, positive for the high-pass filter, negative for the low-pass filter. And so that's what we expect to see around 1K. So I've got both of my cutoff frequencies set to around 1K, and I'll put my cursor right at 1K. And let's see what we see. Well, we've got these symmetrical shapes happening, right? But in opposite directions. So blue here in the magnitude, we see my low-pass filter, and red, my high-pass filter. But the cutoff frequencies, they're both at minus 6 dB. So that's cool to see these two just lined up. And now we see in the phase up here exactly the same slopes, but just 180 degrees apart, right? So if half of this graph is 180 degrees from 0 to negative 180 or 0 to positive 180, I can just pretty easily see this is half a graph. And I can also just see over here on my cursor display that it says 180 degrees. Not exactly, because remember I left them slightly misaligned, and I'll show you why. Because now I'm going to hit the polarity inversion, and what do we expect to happen? That we expect to see this red phase trace up here flip by 180 degrees. We're going to add 180 degrees to this, so we should see it flip around and be right on top of this guy, right? Because it's going to wrap around the phase graph. And there we go. And now you can see why I left them slightly misaligned, so that we could still see them, otherwise if they were perfectly on top of each other, we wouldn't be able to see both of them at the same time. Okay, so this is interesting. So second order Linkowitz-Riley 12 dB per octave filter with a polarity inversion. Now we can see that their phase slope is matching, and the phase slope is matching, and the phase traces are exactly matching when you have a polarity inversion. Okay, let's take this one step further, because this shape is I recognize this shape. It reminds me of something. So I'm looking at this shape and I'm thinking, I think I've seen this before. So let's head over to channel 3. Let's mute everything. And let's unmute this guy. Look at this shape. What is this? So up here we've got a flat magnitude trace, microphone cable. But down here we have this kind of shape, which we just saw over in the other two channels. But there's nothing happening in the magnitude. We see that we have phase shift of 90 degrees right here at the cutoff frequency. And so what this is a first order all pass filter at 1000 hertz. So if I disable it, it goes back to flat. You can't see it because it's, you can't see me pointing. It's under the red line here, okay? But if I enable it, and I can actually move it around to prove this. Is it this guy here? Yes, okay. So you see the green phase trace moving around. So I'm going to offset it a little bit from 1000, and I'm going to turn back on the other two traces. Active all. Okay, so they're not all on top of each other, so you should be able to see that there are 3 phase traces here. 1, 2, 3. And they are all now exactly the same. So it's just interesting to see that this Linkowitz-Riley second order 12 dB per octave filter, or it could be, it doesn't have to necessarily be Linkowitz-Riley for them to be matching phase traces here. But in this case, we're just taking a look at these 3 filters, which are all in the phase exactly the same in this case. So second order filter and a first order all pass filter. And so I don't know if this helps you guys, but for me, just seeing the relationships between these things helps me kind of see how they are related. Let's do the same thing now, but let's jump to a steeper filter. So I'm going to mute this guy. Let's head back over to channel 1. Let's mute everything, and then I'll just unmute channel 1. Okay. So remember, channel 1 is our all-pass filter. I'm going to take out the polarity inversion. So remember, this is our phase shape that we've created here. 90 degrees of phase shift at the cutoff frequency. Let's make this steeper. Let's double it. So right now we are at a second order 12 dB per octave Linkowitz-Riley. Let's go to a fourth order 24 dB per octave. And you saw the phase trace here change. And now it's doubled in its phase shift, right? So we were at a 90 degree phase shift up here, and now it's shot up here to 360 degrees. So we have 360 degrees. I have positive phase shift here now in this high pass filter. And, I just remembered that you guys might be chatting in, so let me see if there are any comments. Hi, Johannes. Hi, Du. Hi, Matt. And Johannes says, all pass filter first order. That's right, you guessed it. And Johannes says, can you invert the all pass filter so you get a flat overall phase? You mean you wanted me to see if they would all add up together? Yes, I could have done that. I tried that earlier. I should have showed you guys. Maybe I can go back and do that in a little bit. Okay, cool. Thanks for chatting in. I just noticed the chat feature. Okay, so we're looking at now a fourth order high pass filter, and we see that the phase shift has doubled. The cutoff frequency has remained the same. So the magnitude got steeper, right? Let's shift back again just to see. Okay, there's a less steep slope, and now there's a steeper slope, but same amount of cut, right? Minus 6 dB at the cutoff frequency, but then it gets steeper as it goes down, and a corresponding steeper slope in the phase, which we can see now wrapping around here. Let's go over to channel 2. Channel 2 has our low pass filter. So I'll unmute channel 2, and remember this is where we left it. It's also at 1,000 hertz, and you can see cutoff frequency right here at 1,000. Magnitude at the cutoff frequencies remain the same, minus 6 dB, but you can see a less steep slope in the magnitude, a less steep slope in the phase. So let's change this to a fourth order, 24 dB per octave, and we see now they match again. Symmetrical, just going here in different directions in the magnitude. But now the phase looks exactly the same. And maybe it becomes more clear why fourth order Linkwitz-Riley filters are so popular, is that they're kind of idiot proof, right? You don't have to remember to do that polarity inversion to make them sum perfectly, at least in the electrical domain. Okay, so we're going to go back to that third channel because this shape also reminds me of something. And you probably know where I'm going to head with this now. So over here, I'll mute this guy. Remember, here's that first order all-pass filter where at the cutoff frequency we had 90 degrees of phase shift in the negative direction, negative 90 degrees here. And so let's double this. Let's go from a first order all-pass filter to a second order all-pass filter. And what I expect to see now at the cutoff frequency is 180 degrees of phase shift instead of only 90. So I'll go to second order filter. There we go. And remember, they're not all perfectly at 1 kilohertz, so we can see them independently here. So exact same shape, right? Same slope in the phase, except the all-pass filter has this flat thing going on through here. And we could even look at the sum here, and we would see them all add up together because they are phase aligned, and we're getting plus 6 dB of summation through here. So channels 1 and 2, they just sum back to 0, right? Because we are basically using symmetrical high and low pass filters. Channel 3 and the magnitude is just flat like a microphone cable, and so all those three channels together add up to plus 6 dB in the magnitude. Okay, so just to review on this second thing here, it's interesting to see, for me at least, it helps my understanding of filters just to see these shapes in action and to see that a fourth order Linkwitz-Riley 24 dB per octave high pass filter and a low pass filter and a second order all pass filter all have the same shape in phase. So this could help me get things done now when I'm doing alignments and I'm trying to think, what filter do I need here? And I can remember the shape and remember the similarities between these things. I think there's one last thing I wanted to share with you guys, which is the bandwidth. I don't know if you can see these tiny numbers down here, but this is a 2 octave wide. The bandwidth is 2. The number is 2 down here. And what's interesting about this is one of the things I'm going to be sharing at this weekend's upcoming workshop is kind of how to look at the bandwidth of not only a single filter, but an entire crossover to try to make some qualitative decisions about whether it is too narrow or too wide. And so here is one of the things I'll be sharing at this weekend's workshop, which is crossover bandwidth, and talking about how wide or narrow the bandwidth itself is and trying to make some decisions about that. So it's just interesting to see here that what I have in this table is that, if you have a filter pair, you're creating a crossover using 24 dB per octave, fourth order filters, that you should expect to see a bandwidth of 2. So also interesting for me to see that this all-pass filter has a bandwidth of 2, and the phase matches here, okay? So that's all I want to share with you guys in today's video. This is the upcoming workshop. It's the Phase Alignment Science Academy. I will put a link to it in the chat. It's this weekend, Sunday and Monday. There'll be 3 sessions each. So when you go to this page and you scroll down here and you click sign up, you'll see that there are 3 different times to pick from on Sunday and Monday. Hopefully one of these times works for you. And if you haven't done it already, there is another course called Intro to the Phase Graph. And that is the kind of, not a prerequisite, but if you haven't taken Intro to the Phase Graph yet, I recommend that you take it. And as an incentive, if you take Intro to the Phase Graph, on the course page, you'll find a discount code for the Phase Alignment Science Academy that'll give you $10 off, I think. So I hope that works as a good incentive. So if you have any questions about what I've shared today, please comment on this video. And if you have any suggestions for me that you think would be good teaching aids, let me know. I'm always looking for like good metaphors, good stories, good questions to ask about how these filter shapes relate. And I'm also just trying to train myself, like I'm trying to help myself remember, what do these shapes look like? What sort of phase shift is going to happen? How's the magnitude going to change when I insert a filter like this? Okay, thanks for joining me, you guys, and hopefully see you at the workshop this weekend. Bye.